Good evening, everyone. This is Astro 10, Celso Batalha, and we are initiating star formation and HR diagram, all these exciting things about stellar evolution and why HR diagram is an important tool that helps us to visualize and understand in which phase, evolutionary phase, a given star happened to be. And for that, I would like to share my screen. So let's do that. There you go. Trisha is having problem with the audio. Are you guys hearing me okay, or it's just Trisha? Rick, can you hear me?
Yeah, oh yeah, yeah. I think Trisha's just muted.
Yeah, Trisha is muted, but she keeps on and on.
I am muted, but once I unmuted, everything cleared up. Now I'm going to mute it again to see if I get to keep the audio.
How is it?
It sounds good.
Okay.
So I'm
all right.
thanks.
This is one of these mysteries of the universe, I think. Okay. So we saw when we studied solar system, we saw under which conditions the sun was formed. So the sun came out of a cloud of gas that, under the action of gravity, this cloud of gas contracted. And as it contracted, it heated up to the point that eventually the central part of the sun became too hot and too dense. And when those two conditions were met, then the sun initiated fusion reactions. And by initiating fusion reactions, the sun was able to produce its own energy. Up to that point, the energy responsible for producing the sunlight or the sun illumination or the sun heat that helped to segregate the planets into terrestrial and Jovians, and I think we went through that subject before. So that light was the result of the sun gravitational potential energy. If you think about gravity, so you have a piece of rock and you let it go, the rock just fall down and it crashes the floor, deforms the floor, so it has energy. And so if you think about now, not just a rock, but uh, several billions and hundreds of billions of little pieces of gas or cells of gas that are falling towards the of uh, center of mass of this newly formed system. So you can think that each cell has its own energy that's going to be transferred to the entire newly formed star, but more particularly in the core. So that energy is being transferred. Eventually, the core hits temperature and densities that uh, allows for the ignition of fusion reactions. But up to that point, this contracting energy was the one responsible for providing the luminosity the sun had up to the point that initiated fusion reaction. So chapter 21 is what happened with other stars, and what happened if a star has an initial mass that is much less than that of the sun, let's say 10%, or by the same token, what would happen with the evolutionary sequence of a star if the initial mass were 10 times as big as that of the sun. So what would be the differences and how the star would behave um, in its evolutionary path? Now, as we try to advance into these questions or fundamental questions, we could remember or could bring into this discussion some of the subjects we learned last week. the properties of stars and the tools that astronomers have to determine these intrinsic properties like surface temperature, metallicity, size, mass, and all these physical quantities we studied last week. So we saw that temperature, the surface temperature of a star is a quantity that can be measured by photometry, if you can use photometry, for instance. But more particularly, the surface temperature of by photometry, I mean color index. You take, you observe the star in different color band, compare them, and then you can have some assessment as to what temperature, surface temperature the star has. But more efficiently, you can use spectroscopy. So spectroscopy can give you a very robust number or limits or boundaries upon which you can establish the star surface temperature. So no problem. The question is, how can we determine how much energy the star itself is putting out in space? So we saw that luminosity is a quantity that depends on the temperature also, but also depends on the size of the star. So stars that have, let's say you have two stars of identical size, so the size of the stars are the same, but one is hotter than the other. So the star that is hotter than will have more energy, will put out more energy in the space, as that energy is proportional to the temperature to the fourth power. So hotter stars of same size, if you have two stars same size, the hotter one will be the most luminous one. And by the same token, if you have stars of same temperature, so now the temperature is the same, but the size is not the same. So one is a supergiant and the other one is a main sequence. So if you compare those two stars, same surface temperature, so the supergiant will be the most luminous one, will be the one producing more energy. So when we hit 1800 and beginning of 1900, astronomers had observed stars nearby and have outlined these properties. So for certain stars, astronomers knew their luminosity and astronomers knew their surface temperature. So it was a natural consequence. In fact, two astronomers did that, Hertzsprung and Russell. They independently they took information about several stars and they coordinate this information in a diagram that now we call HR diagram or Hertzsprung-Russell diagram. So the point of this lecture, I think the highlight of this lecture is HR diagram, which is an evolutionary diagram. So let's go through sections 2.1 and 2.2, and then the planets also the planets. This chapter also visit the exoplanet, not only the history of the exoplanet, but the main finds, the main current finds with respect to exoplanets. According to research done by Kepler satellite, what are the most likely population of exoplanets out there? And that's going to be pretty much the delivery of today's discussion. So what is being shown here is, in fact, this region here is right there. So see those two tiny stars over here, they're over there. And you have a bright one, which is over there. So what these pillars, called the pillars of creation, it's a nice poetical name to describe a site of star formation, which includes a bunch of cold gas, and cold gas is an important and fundamental ingredients for star formation. If the gas is hot, the hot gas has the tendency of having too much internal energy and won't contract. So cold gas, once gravity kicks in, gravity will be able to overcome the natural repulsion, which originates by pretty much collision and thermal energy in a gas. So cold gas is an ingredient for star formation, and cold gas also implies the gas has certain percentage of dust, and dust, grains of dust, is a telltale of low temperature of the gas, and by the same token, if it's a gas of low temperature, then it's a gas that will be forming stars. So the galaxy has thousands of molecular clouds or giant molecular clouds. So they are similar to what we have in our atmosphere as far as air mass. So you have these gigantic systems of air mass that move from the polar to the equator. So these giant molecular clouds in the galaxy itself, they kind of go around the galactic center and they interact among themselves, and they also are subjected to density waves that come out of the galactic center. And these giant molecular clouds, if the conditions are just right, they will initiate star formation. So it's not just one star, but it forms stars in association, which carries dozens or hundreds of stars spread out over the dimensions of the cloud, or clusters, which are more concentrated systems where hundreds of stars happen to be loosely bound by gravitational forces. So open clusters like Pleiades, for instance, like perhaps the cluster that initiated or gave rise to the sun, some astronomers have indicated that the sun itself was part of a cluster, and as the cluster evolved, these stars dispersed, and eventually each one took its own route in the galaxy. But open clusters are stars that are already formed, and they are igniting fusion reactions in their core. So for all purposes, they are pretty much mature stars, but they are loosely bound. And eventually, as these clusters they evolve and they age, these stars will eventually disperse and be all over the place. So giant molecular clouds is an important term. So take notes. I don't know if you notes, but I try in midterm number 2 to get more of the OpenStax material and put in the midterm. I don't know if you notes that. And so take notes of giant molecular clouds. This is an important term, and you might find it again in your midterm number 3 somehow. So Orion molecular clouds, if you had the opportunity of visiting Montgomery Hill Observatory in the last few stargazings, Orion was there. Even this past Friday, a little bit more to the west, right, Rick? But Orion still could be visible. So Orion is a site of star formation. If you look with the naked eye, this is what you see. In fact, let me see if I can bring that on to what is to us. There you go. April 14. Now we are 16. That's the Starry Night. That's today. Let's go to 9 p.m. So this is the sky about 9:20. So Orion is pretty much.
Celso?
Yes. Oh, you lost, right?
Yeah, wait a second. We don't see yours.
Okay, wait a second. Let me take care of that.
We're looking at the stick figures.
Okay, wait a second. What do I need to do? I have to stop sharing, and I have to share again. Let's share the whole desktop. There you go. And then we go to Starry Night. Can you see now?
Yeah.
Okay. So now we go to 920, and so the different, in fact, let's just go back to the question of surface temperature. If you look closely, if the transmission is all right, you see some stars are kind of a reddish like this one, and some others are not, are kind of a more whitish like this one. So if you look at their temperature, so Sirius is a good, let's say 9,000 Kelvin. And if you take it, this star looks like yellowish. Just by looking, if you happen to spy on it, you might determine this star has less temperature, like 3,500 instead of a 9,000. So this color as an indicator of temperature comes from photometry, which I was mentioning before. We are using our eyes to here have a first guess of temperature, but in reality, you can use photometry taking at different color bands and compare the intensity of these color bands to have a direct assessment to the star surface temperature. Like let me see another cool star right here. Let's see if I can pick up that one. Not so much. How about this one? Yeah, 4,500. And if I want to get a hot star, I might take this one here. Where is it? There you go, 20,000. 20,000 is a hot star. Okay, it's a B star. But let me show you Orion. Orion, if you now wait, the sun goes down and past twilight, by 9:20 or so, it's gonna be dark. If you had a nice view of your western sky, Orion is pretty much down. Probably you could see at 9 o'clock maybe, but with some twilight. Now, if we zoom in, or with aid of a telescope, then these clouds can be observed. In fact, this entire region in Orion is a site of star formation. Let's see if I can improve resolution here. Probably not. Yeah, you see that slowly the sky is moving as a result of Earth rotation. But this fuzziness in here, this fuzziness is pretty much clouds. And this pinkish coloration, for those of you who are taking the Astronomy 10L lab, this pinkish coloration here is H alpha, or Balmer alpha. That transition we saw in the lab. That was last week, the Balmer transition from the hydrogen level N equal 3 to the level N equal 2. So you can see also that there are some dark patches here and there, and these dark patches are clouds with a growing density of grains, and these grains are absorbing the light that comes from background stars, and therefore preventing these lights to go through and pretty much being absorbed. And then we see this as these dark patches. and you can see here and there throughout the site. So basically, you have for this Balmer transition to occur, you have to have a star responsible for that, and the star is one of these stars right here. Is a oh, the sky keep moving. Is one of them. Is the hottest one, which is it's not a B star, is an O star. Let me see if I can find the O star, which is the hottest one, is responsible for producing and lighting up the entire nebula. It's not there, and the sky is moving, and I'm not being able to. Oh, that's the trapezium right there. Let me see if I can stop this. Okay, I hope I can get a star. Let me see all the data. Yeah, 9,000 is more like an A star. Well, I lost it. But anyway, you saw 4 stars. One of these stars is a no star, which is the one responsible for lighting up the nebula itself. Now I don't know what I'm looking at. Orion is gone.
1048.
Oh, 1048? Okay, that's it. Let's get out of here.
You lost it.
Time to close the observatory. Go home. All right, so this is Orion, and in fact, if we have a microwave technology, or if you go to space and use infrared detector, that's what been showing here. So we have clouds all over the place, so which indicates this entire region is in fact is still populated by the original gas that gave rise to all these stars. The more picture or more, oh, that's the same Orion Nebula right here. So more nebula, this looks like the trapezium in there. And here you have it all. You have the pinkish hydrogen transition, the Balmer line. You have the dark patches here and there indicating pretty much dust. You have tons of stars, not tons of stars, I'm using a bad communication here, but you have several stars formed as a cluster, and it is so happen that if you can better study them if you have infrared technology, because the infrared detectors are able to better constrain and to better observe, to better derive properties of cold gas. And stars are formed out of cold gas. So what's the main take-home information here? You want to form stars and you want to see stars being formed, you have to go to regions where cold gas exists. And not only that, you gotta have also conditions for gravity to overcome gas pressure, which means the density of the gas or the content of the gas has to be high enough so that it becomes self-attractive. So self-gravity, or the gravity of this gas, will efficiently take the gas to a central point, and eventually a star or a group of stars will be formed. Now, what gives rise to star formation? There are several mechanisms for that. So again, you have the gas, and you need, if you have a trigger mechanism that can initiate contraction, then efficiently lots of stars might be formed at the same time. Later on, when we study galaxies or spiral galaxies in general, one of the main topics we are going to study is how spiral arms are formed. And there are two major theories. One is that if you have a star formation going on, then spiral arms might come up. But another theory, which is pretty much supported by evidence, is when you have two galaxies interacting, so there is an exchange of gravitational energy between those two galaxies, and one of them will take this gravitational energy in its core and spread outward in what's called density waves. And these density waves contract and increase the density in certain regions along the galactic plane. So if a giant molecular clouds happen to enter this region of high density waves, if you will, gas will initiate contraction, and then an episode of star formation will occur. So they have a bunch of stars being formed as these giant molecular clouds go into the density waves. Now, the rate in which these fusion reactions take place in the core, which means the speed in which these fusion reactions take place, or the speed in which hydrogen in the core is depleted. So if fusion reactions in the core happens too fast, hydrogen will be depleted quickly and the star will lose its source of energy, because hydrogen fusion is the source of energy, as we studied in the chapter about the sun. So if that is lost, the star is initiating its demise. The star is initiating its death, if I could use this word to describe that. But the speed in which these reactions takes place depends on the mass of the star. So if the star is massive, 10 solar mass, 20 solar mass, then the pressure on the core is going to be much larger than it is currently in the sun. And therefore, the speed in which this... Hello? You're not following? Hello?
Yeah, you were frozen.
Oh, am I back?
Yeah.
Okay. So what I was mentioning is the speed in which these fusion reactions take place in the core depends on the mass of the star. So if the mass is too much, like 20 solar mass, then the pressure on the core will be such the hydrogen will deplete quickly. The star will live a short life. So massive stars have a short life, and low mass stars have a long life. They live and prosper, right? So that's the idea. So let me just quickly turn on the light here. I'm getting dark. So if you have if a giant molecular cloud happen to be subject to star formation, in which hundreds of stars are formed at the same time, because the process triggering the star formation is the same and is applied to an entire giant molecular cloud. If this happens, then the most massive stars will die out quicker than the low mass stars, which is counterintuitive if you think. So when we observe clusters of young stars, in general, the massive ones, the O stars, the most massive stars called O or B stars, they will evolve quickly. And then in no time, they are gone. They are out of, they have completed their cycle. They are done with their business. And whereas the low mass stars, they might still be going under the contraction mode, trying to slowly move towards the main sequence, and initiate their fusion reactions. So sometimes we look at a cluster of stars, and most of them are low mass stars. We don't see high mass stars. It means that cluster had no high mass stars to begin with. The answer is no. I mean, these high mass stars are gone. They are dead. So mass is the most important element controlling stellar evolution. And this topic is so important that I put it in one of the upcoming discussions. So what triggers, what governs stellar evolution is the initial mass of the star. Low mass stars, they go by their lives too slowly. They take their time. They contract slowly. They burn fusion to helium slowly when they are in the main sequence. And they die out slowly. Whereas high mass stars, like old stars, they contract quickly. They go through the main sequence quickly. And they have an explosive death. And we call that supernova.
So,
now, yes.
What will make, okay, we know a high mass star burns through their fuel faster, correct?
Yes.
But what will make a star massive if there's more gas in the beginning?
If there is more gas in the very beginning, if the initial density of that gas was big enough, that would result in a 30 solar mass star.
Okay, so it's like someone keeps going to McDonald's and getting Big Macs every day.
I don't know if there is a McDonald's out there in the space, but
well, as an analogy,
it might have an old McDonald's somewhere playing all these tricks, but I don't know. But you could think that way. See, I mean, if okay, maybe we could rethink the analogy, because let's say we all born with a certain amount of mass, right? And then we grow our mass if we eat a lot of a McDonald's. That's true.
Yeah.
So stars, they don't grow their mass as they live. In fact, they are born with that initial mass.
Yeah, right. But don't they, when they start collecting all the gas, they collect as much as they can around them?
The gas, certain. So imagine there is a river of gas. It's a giant molecular cloud, and here and there, like in this, in the pillars of creation.
Yeah, yeah.
Yeah. So here and there, see this little.
Like a tube.
Like a, what you would say, a tube?
Well, it looks like a tube of gas.
Yeah, this little dot over here. This is a little cocoon where a star happened to be formed.
Okay.
So, which means if the density is just right, then because see, the gas of this entire pillar will not contract because it's kept stable by gas pressure. So the pressure of the gas itself, although very thin, is just right to keep this pillar the way it is. But let's say that one star somewhere nearby explodes.
Right.
And when this star explodes, it's going to generate shock waves through the giant molecular cloud. So when the shock waves hit this pillar, it's going to contract certain regions. Once contract, it might reach the density just right for gravity to kick in. And when gravity kicks in, now the collapse is on the way and cannot be stopped. Now, when these density waves pass through the glass, through the pillar, it might hit some region that has some initial density good enough to produce, as an end result, a 30 solar mass star.
Okay.
But in general, the probability of forming large mass star is very low. I mean, most of the stars formed by this type of process are low mass stars. Stars that are subsolar as far as mass is concerned. It seems that nature likes to form small stars. Like if we advance towards the exoplanet sections, it seems that nature preferred to form small planets rather than the giant Jupiter-sized planets. Most of the planets, the exoplanets found so far in this research done by Kepler, now TESS was launched. It's another satellite that's gonna carry on the legacy of Kepler, and is going to do the survey not just in one region but the entire sky, and what we are going to I mean expect to confirm is that most of the planets out there are so-called super Earth. They are somewhere in between the mass of a Earth and mass of a Jupiter, somewhere in between. So it seems that nature preferred the little things rather than the big things. But here's an example of a molecular cloud. So we have a molecular cloud, and so there is a star forming process going on, and then eventually one of the stars formed go through the evolutionary process that lead to an explosion because it's a high mass star. This explosion will trigger shock waves. These shock waves passing through the molecular clouds will trigger more star formations. So the tendency is, as the universe age, giant molecular clouds will be eventually depleted of their cold gas because the stars will be formed, and when the stars die, material is released back to the interstellar medium, but much less than was originally available. So, and as a result, also, for those of you who went to the Astro 10L course, one of the main results of stellar evolution is the production of a newly formed atoms. This is a process by which the universe in large scale becomes more metal-rich as it ages, because the stars keep on being formed, stars keep on dying, and low-mass stars will efficiently produce carbon and oxygen, and high-mass stars will produce the remaining heavy metals. So more stars being formed, and more stars die, and more metals are produced. So the universe age, which with more metals available. So we couldn't exist in the very few billion years in the history of our universe, at least being the way we are, because we require certain metallicity that was only possible after 13 billion years into the life of the universe. And that is the main kind of a standard model of star formation. So you have a clump of gas, relatively large, 5,000 AU, if you will, and then gravity takes place, and then contraction takes place. Now, not only gravity takes place, but also we have to include in this narrative the star itself, or this clump itself, has some initial rotation, and astronomers address that and name that as angular momentum. So the angular momentum of this gas is the one responsible for flattening this circumstellar disk, as we can see here in the slide B. So gas falls not necessarily directly towards the star, but depending on the angle where the cell of gas is, if you can follow my cursor, the gas will fall towards the circumstellar disk, and then from the circumstellar disk will spiral and fall onto the star. So eventually, the star that falls through the disk, 10% or so of that, in fact 90% or so of the gas that falls in the disk will spiral and eventually settle in the central star. Now, depending on also the density of this disk, the star will initiate this bipolar flow. See this red line coming out of the poles? So these three red lines coming out of the pole is pretty much an indicator of bipolar flow. So pictures of young star systems are like that. Look at this. So we have a disk, and what we are seeing here is the so-called HH object, or Herbig-Haro object. There are two astronomers, Herbig and Haro are two different astronomers, but they studied these objects, and what we are seeing here is a disk. So we are looking at this disk almost edge on. This black part that goes through the central part of the disk is pretty much the result of dust that still exists in the disk and blocks the light of the disk itself. But the disk is spiraling and falling towards the star, but some of this material is ejected in two flows, and we call that bipolar flow. And you see how they become different here. It seems my connection has failed. More of bipolar flow to the right and left. So the star happens to be in the very center. Another one here, and more in here. So all this darkness that goes through the bright region is pretty much the disk. So the disk is right here, it's going across, as we can see. Okay, HR diagram. So what HR diagram really is? Here it is. It's a diagram that relates luminosity, and we saw previously that luminosity is the intrinsic energy the star itself is capable of sending out to the interstellar medium related to its surface temperature. Okay, so now imagine late 1800, beginning 1900, astronomers have developed spectroscopy, and they are clever enough with photometry to the point they can pretty much have with some accuracy the total energy of a star and its surface temperature. And when they put in a diagram, they find something interesting. 90% of the stars happen to be located in this kind of a reddish locale, which here is indicated as zero age main sequence, but is the main sequence. So 90% of the stars in our galaxy, or 90% of the stars, in fact, we observe that in our vicinity, 90%, 90% of the stars happen to be in this locale main sequence. They run from low temperature to high temperature from the lower right-hand side to the upper left-hand side. See that? And these black lines here, so we have one, the second one, third, fourth, fifth, sixth. These black lines are called evolutionary tracks. Evolutionary tracks. So what exactly, how can we read this evolutionary track? This evolutionary track is a theoretical calculation based on models primarily. I mean, we cannot follow the star luminosity and how much that luminosity change in respect to its surface temperature over several millions of years, right? We will not live that long. A star like the sun undergo contraction since the moment it was a spread out gas in the interstellar medium, or perhaps in the bosom of a giant molecular cloud. The sun took 20 million years, 20 million years, to contract to the point of igniting its fusion reactions. So we call the phase in which the star is undergoing contraction pre pre-main sequence stars. Why pre-main sequence stars? Because it's prior to the point they reach what we call main sequence. And the point when they exactly ignite fusion reaction in their core, that point is called zero age main sequence. So they are initiating their life in the main sequence by initiating the fusion reactions of hydrogen in their very core. So pre-main sequence, or PMS, pre-main sequence phase, are phases in the star life in which gas was efficiently brought to a central part by gravity force. The contraction took place. So the star is contracting and will end this contraction when fusion reactions initiate or are ignited in the very core of the star. So this track is theoretical. So somebody, you go to the physicist or to the astronomer and say, listen, I observe these stars have a certain percentage of carbon, certain percentage of magnesium, titanium, so on, so on, so on. And then with that information, astronomers can use equations of mass continuity of mass, how radio um, uh, like light, how electromagnetic radiation propagates from the core all the way to the surface, how the pressure is distributed over the interior part, how opacity, which is the ability of certain atoms and molecules to retrieve light and keep the gas hot. So all that information that physicists and astronomers know about gas are used to create these tracks. And then what astronomers do, they observe stars and see if their observations match theory. And now there is a feedback mechanism or communication between theoretical astronomers and observational astronomers. And they exchange information, and that information is used to calibrate the models. So basically, models don't dictate what we observe, the other way around. What we observe dictate how models should behave. And then more stars were observed in the 20s and 30s and 40s, better model were developed. But how do we read this? If you take one solar mass star like our sun, so this solar mass star initiated its life with a luminosity that is about 100 times as luminous as the sun, right? And then that star slowly contract. See, and the temperature was 4,000 Kelvin. And then that star contract, and heats up to the point that eventually turn around, and there is a lot of details here which we don't cover, in the way the energy is migrated from the core to the surface by convection or by radiation. But eventually the fusion reactions take place, and then the star finally reach the zero age main sequence. Okay. Now, a 100 solar mass star, very massive one, those babies are hard to find. They contract quickly, right? And they quickly reach their main sequence. So those tracks are pre-main sequence. And in future chapters, in fact, next week, we are going to see the reversal of that. So once the stars reach the main sequence, now the fuel that feeds the star, that produce energy and make the star shine for 90% of or 80% of its lifetime, that fuel is going to be gone. Hydrogen is going to be gone. And when this happens, the star will move out of main sequence. And we call that the pause-main sequence phase. So we have a pre-main sequence phase, and we have a pause-main sequence phase, in which the star becomes asymptotic giant branch stars, or becomes a giant stars or supergiant, and then we have these different classes. Okay. So this type of stars, they are prima in sequence, they have specific names. Herbig-Haro objects are those that has this bipolar flow, but then eventually this bipolar flow uh, settles down, and the star can become, depending on its mass, a T-Tauri star or a Herbig AEBE star, depending on the mass of the star itself. And the spectral signatures, the way the star will appear to you, will also be different. And the way gas will find its way to the star will differ as well. Okay. Quickly about planets around. So the stars have a disk, as we saw here, right? And if these young stars have disk, then chances are this disk will be the site of planet formation. And then what comes next is a study on exoplanets and the work done by the radio velocity groups that use Doppler effect to find exoplanets, and because of a bias in the observation, the technique used, most of the planets detected with the radio velocity techniques were Jupiter size because they were close to the stars, they were tugging the stars were moving, and then you could detect that motion with Doppler effect techniques. Kepler came in, and with it, its ability to measure with high precision the dimming of the light of the starlight when a planet passes in front of the star disk. And by doing so, astronomers can determine how large the planet is, how far it is from the star itself, and especially if you can detect this transit on and on and on, and then it can determine the size of the orbits and so on and so on. So basically, if we jump further down here, that's the Doppler effect technique. And that is Kepler. And that is what Kepler found. So basically, if you look at these blue dots, those are planets found by the radio velocity technique. The yellow dots are observations found by Kepler, and 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 here is Earth analogs, right? And here Neptune analogs and Jupiter analogs. And here is what we, after all these planets being corrected by their sizes and densities and everything, this is where most of them peak. They are called super Earth. So the size is about 1.4 to 2.8 Earth radius. That's where most of them are supposed to be found. So Jupiter is somewhere here. This is Jupiter. So there is not a lot of equivalent in this research. All right. So again, in Star Evolution, it's gonna be continuing next week with trying to answer the following questions. So once hydrogen in the core is exhausted, what's gonna happen? So what are the following up or the outcome of the depletion of fuel? The outcome is gonna be three things: white dwarf, neutron star, or black hole. If it's a neutron star or a black hole, there will be explosion, we call supernovae. And if it is just a low mass star, which results in a white dwarf, then the death is a little bit mild. All right. So pretty much that's it. I think I extended because the astrobiological periodic table is important, and extended um, this discussion to another week, so we have more time to dive into the table itself and try to get more information and learn something about it. It's a very cool subject that we should invest more time. Okay. Okay, so I will stop taping for now. Good night to all of you.